In this video, we're going to talk about the distance from a point to a plane. So, for example, if P is a point on a plane with a normal vector n, then the distance from any point P to some point S in space, so the distance from that point on the plane to S in space, is defined as the length of the vector projection of PS onto N. And the way we write that, D, that distance, is the magnitude of the vector PS dotted with the unit normal vector. So just restating the distance from some point S to a plane with a normal vector at point P. That distance is given by the magnitude of PS, the vector from P to S, dotted with that normal vector divided by its magnitude. And anytime we're dividing that, a vector by its own magnitude, we're getting a unit vector. So let's look at an example. And one thing you're going to notice is this is that same plane we were talking about earlier. 001, 200, 030. So we were talking about this plane, which is running through those points. And P is this point here. Of course, I've drawn the plane as a triangle, but the plane actually spreads out in space infinitely in all directions. Just like when you draw the line, it extends in all directions as well. So for this example, we're going to find the distance from the point S to the plane, 3x plus 2y plus 6z equals 6. So the first thing we need to do is note this point P on the plane. So we can find any point on the plane, and we're going to use this given point, which we've already been talking about. But if we weren't given a point and we needed to find one, well, we can just do that by finding an intercept. So find any point on the plane. That would be an axis intercept. And in order for us to find that axis intercept, in this case, we would say let x equal 0 and, we know the y value, z equals 0. If I plug that into my equation, 3 times 0 plus 2y plus 6 times 0 equals 6 gives me that 2y equals 6, or rather, y equals 3. So that's where that point comes from if it's not given to you. So we have this point on the plane which represents a y-intercept. And we know what our normal vector n is. We know that n is 3i plus 2j plus 6k. Also, since we know both P and S, we can calculate the vector which originates at P and terminates at S. So subtracting the components, S minus P, 1 minus 0, I've got 1i, 1 minus 3 minus 2j, and 3 minus 0 plus 3k. So I minus 2j plus 3k. Now, considering the formula that we stated at the start of this, that distance between the point to the plane was going to be the dot product of that vector, PS. We want it dotted with the unit vector for this normal vector. That's going to give us this projection, which tells us the distance, specifically the shortest distance from S to that plane. So regardless, we need to know the magnitude of n, the magnitude of n, which is the square root of 3 squared plus 2 squared plus 6 squared, or the square root of 49, the magnitude of the n vector is 7. So then the unit for my normal vector is 3i plus 2j plus 6k over 7, or 3/7 I plus 2/7 j plus 6/7 k. So this is the dot product. In order to find that distance, we need the magnitude of the dot product from PS dotted with n over the magnitude of n. So that is I minus 2j plus 3k, the vector PS, dotted with the unit vector that's perpendicular, 3/7 I plus 2/7 j plus 6/7 k. So we've been doing a lot of cross products. This is a dot product here. That's just 1 times 3/7 plus -2 times 2/7 plus 3 times 6/7. We're going to find the magnitude of that. That gives me 3/7 minus 4/7 plus 18/7. 3 minus 4, -1. So that is the magnitude of the scalar 17/7, or just 17/7 the magnitude, or we could think, since it's a scalar, absolute value. So 17/7 is the distance from the point S straight down to the plane that we were dealing with. We have one more example we're going to do in this video, and it's a quick formula for the angle between planes. We have one more formula here, and that is for determining the angle between two planes. So that would be the angle between the normal vectors. So we can determine that theta, it's going to be cosine inverse of the argument, normal vector 1 dotted with normal vector 2, divided by the magnitude of normal 1 times the magnitude of normal 2. So for this example, we're going to find the angle between the planes. And in order to do that, we need to know what both of the normal vectors are, as well as their magnitudes and the dot product of the two normal vectors. So normal vector 1 is 5i plus j minus k. The magnitude of normal vector 1 is the square root of 5 squared plus 1 squared plus 1 squared, or the square root of 27. Normal vector 2 is 1i minus 2j plus 3k. And the magnitude of normal vector 2 is 1 squared plus 2 squared, 4, 5, plus 3 squared, 9. We end up with the square root of 14. So those are my magnitudes. Let's find our dot product. So n1 dotted with n2. That's going to be 5 times 1 plus 1 times -2 plus -1 times 3. 5 minus 2 minus 3 equals 0. So, using our formula, my dot product is 0, n sub 1, 27, or root 27, magnitude of n sub 2 is root 14. So theta equals cosine inverse of 0 over root 27 times root 14. And of course, this problem is nice because that argument simplifies to 0. Cosine inverse of 0, where is cosine equal to 0? At theta equals pi over 2 radians, or 90 degrees. So, what does that tell you? These two planes are perpendicular. And that's the formula for determining the angle between two planes.